what happens when researchers succeed in building the first general artificial intelligence? Tonight, Adrian and I, Kaspar, will not give you the answer to this question, but we'll try to give you some arguments, some considerations that show what the future might hold regarding artificial intelligence. As I said, my name is Kaspar. I studied computer science at ETH Zurich. I've been looking into this topic for 3 years now.
Yeah, my name is Adrian. I've studied physics at ETH Zurich, and then I'm doing a PhD in theoretical physics at the University of Basel. And you will meet me again later on.
Yeah, so when it comes to the outline, so first I will define a few important terms. I will introduce the topic, kind of the theoretic phenomena called technological singularity. Adrian will continue with some considerations where this might lead us to, some outcomes, and also where we are today and potential path towards such a superintelligence. And then I will conclude with some strategic considerations, what needs to be done facing such an outlook. So what are we talking about? First of all, it's always useful to have a definition. So for the sake of this presentation, I define intelligence as a measure for an agent's ability to achieve its goal in a wide range of unknown environments. So this is a totally technical definition. It might not capture everything that you're familiar with when it comes to the term intelligence. If you're confused about this term intelligence during this presentation, just replace it with optimization power. So it's just about kind of fulfilling your goal in whatever environment you happen to be in. So all that is needed to have such an intelligence is an epistemology. So you need to have a learning mechanism to learn a model about the world, about the environment you act in. Secondly, you need to have an utility function to rate between different world states. So you need to have a way for your decisions, have a criteria how you decide. And this is the last ingredient. So you need to have a decision theory, how you're going to decide with the model of the world. So you have a model, what your interactions will lead you to, and then you decide, according to your utility function, which actions you're going to take. So this all sounds very simple. In a certain sense it is, but only if you're, as an agent, kind of live outside of this environment. So when you become part of the environment, there are many open problems, and we will not go into them tonight. A first very important remark is we're talking about intelligence tonight, we're not talking about consciousness. So this is a totally separate question. So consciousness is not required for an agent to reshape the world according to its utility function. But it's still interesting. So consciousness is either reducible, so it can be broken up into other parts. So it might be emergent phenomena of an intelligent agent, or it might be fundamental, and kind of independent of that, it might also be a universal property of this universe. In the same kind of topic also falls machine sentience. So does it feel like anything to be such a machine, such an intelligent machine? This is an open question, and it's of immense importance. So there are two main aspects of this question. So can simulated entities be conscious? And the second, which is kind of obviously true, is if the first is true, can machines also be moral patients? So do we need to take care of these machines? Do they deserve moral consideration? And if consciousness can be simulated, this might kind of change our metaphysical outlook on this universe. So we might, in principle, live in a computer simulation. So before entering the actual arguments, let's zoom out a little bit. Oxford professor Nick Bostrom coined the term crucial consideration. So a crucial consideration is an idea that entails a major change regarding your priorities, regarding your actions. And why are crucial considerations so important? So if you're heading the wrong way, yeah, the last thing you want to have is progress. So I claim that we cover quite a few potential crucial considerations tonight. And I will start now with the first one. So when you look on the history of the universe, it is still presumably, or there was presumably something like a Big Bang, and now 14 billion years later, we're kind of 4 billion years into this life period when life first emerged 4 billion years ago. So you have the time on the x-axis, and you have some kind of general notion of the maturity of life on the y-axis. So currently we are here, and if you look back on the past decades, centuries, millennia, a lot of things have changed quite dramatically. So the argument is we're not living in a stable time. So it's not the same as it always was, and therefore it will likely not stay the same as we currently are now. Now we live now kind of in really big historical terms, kind of in an unstable time. So it's very unlikely that we will stay in this situation forever. Now, how can you kind of look far into the future? So the argument is that there are certain states that kind of act as an attractor. So one example is if life goes extinct, it kind of tends to stay extinct. So once you're down here, it's done. So this is an attractor state. You remain extinct, and the other kind of direction would be technological maturity, kind of having a system that is able to self-sustain. So I have a term there called singleton. So what might such technological maturity look like? So first definition of this term singleton, which was also coined by Professor Nick Bostrom. So a singleton is a world order with a single decision-making agency at its highest level. And it's very crucial that the definition itself leaves it open what this single decision agency might be. So it might be anything from just kind of a society with strong pro-social punishment. It might be kind of a one-party totalitarian regime, or it might be something like a superintelligent agent, as we're going to talk tonight. And so it's also kind of the second assumption there is that such a singleton is smart enough to avoid internal and external threats to its persistence. So once you are in a singleton, you stay there. So that's just kind of the definition. Now, what are the advantages? So there are two of them, or kind of two main advantages. So first of all the cooperation problems are solved. And one of the cooperation problems are arms races, and also kind of the Darwinian nature of the universe we live in. So that the stronger survival of the fittest might no longer be true, which might be very well a good thing. There are also some disadvantages. So you put all the eggs into one basket. So if kind of the singleton goes bad, it could result in a dystopian world, and you would have a durable lock-in. And then there's this general question which is called the singleton hypothesis. So and the question there is this our ultimate fate? So if you look back, we had increasingly an organization on higher and higher levels. So from tribes to national states to international and supranational organizations. And this is just kind of the natural continuation of past trends. So the second part of this presentation is about this term, which some of you might have heard of, called singularity. So this whole presentation is an abbreviation of a longer one, so we've just picked kind of the main aspects and try to bring the argument across. So first observation is that the more knowledge you have, the more powerful the technologies are that you can build, and the more powerful your technologies are, the more knowledge you can acquire. So what does it mean? It means that progress feeds on itself. And if you look on the history of technology, again, it's kind of a very general notion here, technology. You could kind of insert whatever particular technology you like. So most of them have some exponential growth in the past. And when it comes to computer speed, this is known as Moore's law, but it's way, way, way broader, this law, than just computer power and speed. So what especially a very Kurzweil argument is that if it's true since kind of the dawn of life, it might also hold true for the next 100 years. So what does it mean if this law, this exponential growth in technology, is true for the 21st century? So the problem is that our intuition is totally linear. And what it means, or what the world might look like at the end of the century. So if you stand here in the year 2000, imagine you would have steady progress. Now imagine where we would be in 20,000 years. Kind of if this progress continues on at a linear rate. And now, kind of due to exponential growth, the argument is we might be there at the end of this century. So don't kind of limit your imagination too much. So, as you know, knowledge and technology is extremely powerful, but so far it was mainly applied to kind of external objects, external things. But what if there is an agent that applies knowledge and technology to itself? So such an agent could bootstrap and amplify its own intelligence. And this is the argument which is known as intelligence explosion. So if an agent is able to improve its own intelligence, and if now with such a kind of proportionality thesis, if this holds true for more than just a few iterations, it might kind of grow extremely fast. Now, as I said, so it's a theoretical argument, so we don't know how kind of intelligence scales. So it might very well be bounded. Yeah, but it's an open question as well. So, but imagine kind of if it's not bounded, and if you have such an intelligence explosion, what we might end with is what is known as technological singularity. So as I said, it's theoretical in the sense it hasn't been observed, but there are arguments, kind of the arguments I gave and more advanced versions of them. And kind of a few people have been pretty influential in kind of coining this term, singularity, and have their own notion attached to it. So the first one, which we shortly covered, is Ray Kurzweil's notion of accelerating change. So kind of all technologies, also nanotechnology, biotechnology, it's just going faster and faster and faster. And when kind of this grow becomes almost vertical, that's where kind of singularity takes place. Another notion which you've also seen is this intelligence explosion, which goes back to Professor H.A. Good. And the third one by computer science professor and science fiction author Werner Winch is that if you have agents that are smarter than you are, you're no longer able to predict the future. And so in that sense, the singularity at that moment in time is an event horizon beyond which we may not look now. So this was the introduction. Now Adrian will cover what is my latest.
Thank you, Kaspar. So at the beginning of the talk, Kaspar has defined what we mean by intelligence. So let me now introduce the term superintelligence. What do we mean by superintelligence? We call an agent superintelligent if it surpasses human at virtually all cognitive tasks and virtually all areas of interest that are kind of cognitive in nature. And it's very important here to realize that there's no reason to assume that our biological brains are in some way close to the physical limitations there are on intelligence. So usually if we think about the range of intelligence there is in the universe, we kind of imagine some fool on the one end of the scale and then Einstein on the other end of the scale. But if you take a step back and look at it a bit in a broader picture, it's important to realize that these 2 points are basically indistinguishable points which correspond to almost the same level of intelligence, and there is a lot of space below this human intelligence level, and there is no reason to think that there is not a lot of space above the human level of intelligence. And if you take this step out, then the whole human scale kind of almost vanishes to a point. So what are possible paths that could potentially lead us to such a superintelligence? So the most promising route probably is artificial intelligence. And when it comes to artificial intelligence, we can distinguish between neuromorphic intelligence. So these are methods of artificial intelligence which are inspired by biology, which are inspired by looking at how nature achieves intelligence. And then there are synthetic methods which have no kind of biological motivation. And so it kind of the extreme of biology-inspired intelligence would be whole brain emulation, which means that you just scan a whole biological brain in very high detail with very high resolution and just simulate this on a computer. So if you like, this is kind of a brute force path towards superintelligence, because it does not require you to understand what the brain actually does. So all it requires is that you're able to scan a brain at a very high resolution and a very high level of accuracy. So if you've heard, for example, about the Blue Brain project at EPFL, that's what they do. And basically, the question whether an artificial path or whole brain emulation will come first kind of depends on how fast our understanding of intelligence progresses. So as I said, this path does not require any understanding of how intelligence works. It's kind of a pure engineering challenge. And then there are other possible ways that one can think about that can somehow increase intelligence, but that will probably not lead us to full superintelligence in a strong sense. So the first of these is just biological brains as we know them, that could potentially be enhanced in some way, but probably will not lead us as far as these ways will lead us. So what I should have said before is that whole brain emulation, of course, gives you the possibility that once you've scanned a brain to computer hardware, you can run it at a much higher speed than is possible in nature. So while in some sense this may not be an actual increase of intelligence, just the fact that you can multiply then the brain and run it at very high speed may in effect lead to similar outcomes than if you were able to actually increase the intelligence of a being. Yeah, and then one can potentially imagine interfaces between biological and computer brains, and finally, in some sense, one can also understand organizations or states as intelligent in some sense, but neither of these is likely to reach full-scale superintelligence. But since these tasks are all in some way social problems, so they're all teams working on them and societies funding these projects, better organizations, better functioning states are certainly helpful in achieving one of these ways. So what are some advantages that computers and hence artificial intelligences have over biological brains? So the first point is size. So brains are basically limited to the size of your skull, and due to the limited size of the birth channel, our brains are unlikely to become much larger. And by contrast, there's no obvious limit to the size a computer could potentially have. Computers can run at much higher speed. So if you look at these numbers here, biological neurons fire 200 times per second, and modern microprocessors can fire 4 billion times a second. Then also the speed of signals. So in the human brains, that's 120 meters per second, which is relatively slow, whereas in a computer, the only limit is the speed of light. And then you can have very reliable memory. Humans tend to have problem memorizing things, as you all know, whereas hard disks are very reliable and have enormous capacities. Then also there's the software aspect. So basically every human needs to learn for the first 2 decades of their life everything from their parents until they are kind of fully, until they function in a full way. And by contrast, once a program has learned something, has achieved some skills, you can just copy and paste it and extend it with further modules and so on. So all these biological limitations are absent on the artificial intelligence level. Then we also know from cognitive science that humans suffer from a huge number of cognitive biases that sometimes prevent us from achieving our goals, and there's no reason why these should be present for artificial intelligences. Another aspect here is also motivation. Humans tend to lose interest in boring tasks after a few hours, and again, there's no reason why this should be the case with artificial intelligences. Now, all of these advantages can give an artificial intelligence a wide range of advantages. So one of these is intelligence amplification that Kaspar talked already about. So an artificial intelligence would have the possibility to further increase its own intelligence. And so given an initial ability to improve its own intelligence, there's no obvious limitation to this self-improving process. And it could also be much better than humans at strategizing, hacking, social manipulation, economic productivity, and technological research. Okay, so now when it comes to thinking about what such a superintelligence will be, there is a very important thesis that has been developed, which is called the Orthogonality Thesis. And what it says is that intelligence, as defined at the beginning of this talk, and final goals are orthogonal in some sense. So basically almost any level of intelligence and almost any goals you could potentially have are compatible. So there's no reason to expect that a sufficiently high level of intelligence will necessarily imply a certain set of goals. So if you like, you can read this orthogonality thesis as kind of a warning. So do not rely on an artificial intelligence being somehow benevolent just because it's intelligent. It can be intelligent and still have goals that can be very destructive for what we value. And another important point here is that there are some goals you can have that are kind of explicitly bad, others that we could call explicitly good, but just almost all goals that you could possibly implement in intelligence are kind of neither good nor bad according to human standards, but just kind of senseless. So here the example would be an agent that tries to maximize the number of paper clips. So if you take a step back and look at all goals that one could possibly pursue, the subset of those goals which are really explicitly bad or explicitly good is just a very small subset, and the vast majority of possible goals is in itself neither good nor bad, but still has implications for what we as humans tend to value. And yeah, because there are just much more goals that are neither good nor bad, the default outcome if we don't make sure that there are good goals implemented, the default outcome will probably not be a bad goal, but just one that pursues something which we would call pointless. Now, it seems that since I've argued that there's such a vast space of possible goals that you could possibly pursue, there's no way of knowing what a superintelligence would possibly do. But in fact, we can possibly still make some educated guesses about what a superintelligence will do, because for almost any goal a superintelligence could have, there are certain sub-goals which would be instrumentally useful towards achieving almost any goal. So the most obvious of these is self-preservation. Any agent pursuing any kind of goal will want to make sure that it continues to exist, because otherwise it will not be able to pursue its goal any further, unless its goal somehow involves its own destruction. And then in a similar point, an agent will try to preserve its own goal structure. So even if it continues to exist physically, if its goals are modified at some later time, that's still harmful for the goals that it has at some earlier time. So it will tend to ensure that its goal structure is preserved. Finally, almost any goals that you could possibly pursue are better pursued if you have more resources at your hand. So most agents will tend to accumulate resources and amplify their own intelligence, which also helps you achieve almost any goal you can have. So what can we conclude from this slide and the previous slide? So because almost for almost all goals you could have, you want to get control of resources, and therefore for almost all goals a superintelligence could have, it will just take to get control of all the resources in its neighborhood, so including everything that is on Earth. So kind of the bottom line of this slide and the previous slide is that you should not trust on there being automatically a good outcome. We will only get a good outcome if we actively take efforts to make sure that there is a good outcome. So one conclusion from this is that our first superhuman intelligence better be a safe one and a good one, because we may only get one shot. And now if you look at humanity's history, we see that historically humans are kind of good at getting things right after failing 1,000 times. And we humans historically were terrible at getting things right at the very first trial. Humans are able to learn, are able to make progress, but often only after catastrophes have occurred. And so if you combine this with this point here, the conclusion seems to be that we better avoid this historic pattern. So now, how can such an evolution towards superintelligence, how will this look like? Now there are two different questions that one can ask. One is, how long is the time from now until the beginning of the takeoff? And then a second independent question is, what's the duration of the takeoff? And the takeoff is here defined as the time from the time when the self-improvement process of an intelligence starts until it reaches a level which is significantly higher than the human intelligence level. And these two questions of the time until takeoff and the duration of the takeoff are kind of independent of each other. Now, the relevance of the first question of the time to the takeoff is kind of obvious. The relevance of the second question may be a bit less obvious. So what's the relevance of the duration of the takeoff? So if the takeoff is very fast, such as a week or a few weeks, there's likely that there will just be one agent that controls the whole neighborhood. So which can then lead to a singleton, a term which Kaspar has introduced. By contrast, if the takeoff is sufficiently slow, then there may be time for different agents with different goals to emerge, which are all kind of similarly powerful, and which then compete and trade with each other. And then this interplay between these different agents will tend to dominate what happens in the future. Okay, so now this was all kind of theoretical and a bit far-fetched. So the next chapter we'll talk about where are we now, what can we already see. So if we look again at biological brains and computers, the hardware of brains is highly parallel. So in your brain there are always a lot of things happening in parallel, and you're conscious of only a few of all of these processes that are happening in parallel. But it appears to you that there's kind of a sequential process of events in your consciousness. So if you like, your consciousness is kind of a sequential user interface on top of a parallel hardware. And then for computers, it's exactly the opposite, or at least has been until quite recently. So traditional CPUs have only been able to do one process after the other, but still you can run several programs in parallel. So kind of your computer provides a parallel user interface on top of a sequential hardware, which is exactly the opposite of the brain. And one implication of this is what is difficult and easy for biological brains and for computers. So pattern recognition is very easy for humans because we have very specialized modules for recognizing patterns, so it goes very effortlessly for us. And by contrast, just processing raw data is very difficult for us. So just multiplying two 5-digit integers in our heads is more than we can do. And again, for computers, it's kind of the opposite. So while every child can recognize a lot of different objects and distinguish them, this is something that is very hard to get computers to do. But by contrast, just processing raw data is something that can be done very easily by use of computers. But in fact, in the recent years, there's been a lot of progress on exactly this point, on computer-based pattern recognitions. So one very recent event from 1 month ago, there was an image recognition contest that has been held for several years now, where you just are given images and have to write a description to them. And now for the first time this year, teams from Google and from Microsoft achieved superhuman performance in this task. And one reason for this is our progresses on the hardware level, so that now people rely no longer on CPUs but on GPUs, which can be used in a highly parallel way. So here's a bit more about the state of the art. We have self-driving cars. Already in 1997, the then best chess player in the world was defeated by IBM's Deep Blue. And in 2011, IBM's Watson even defeated the two best players in the game Jeopardy, which is a game where you're given an answer, and then you have to find a question which has this answer as its answer. So here's the traffic sign recognition contest, and you probably cannot read it, but on the first place here is a team from Switzerland. There's in Lugano, there's the Swiss AI lab, which is led by Jürgen Schmidhuber, was on the first place, so of course not the team itself, but the artificial intelligence that they programmed, and humans here were on the second place. Okay, now here you can see something very recently. From this institute in Lugano, several alumni of this institute have founded a company which is called DeepMind, which was acquired by Google like 1 or 2 years ago for about $400 million. It's now in London, and here you can see something what their artificial intelligence can do. So they let it play a variety of games, and what is very important is that they do not program into the intelligence how to play these games. All the program receives are the pixels of the screen and the reward telling it how good it performed. So at the beginning it tends to make some random moves. It just presses buttons at random and it sees now this works, this didn't work, and then it progresses and progresses, and in a lot of these games they reach a superhuman performance. So let's see how this works. Yeah, so this is after 100 episodes. Yeah, it makes some random moves and the ball often goes down. Now after 200 episodes it has realized that it shouldn't let the ball go down, but it still makes mistakes. Yeah, now after 400 episodes it doesn't let the ball down anymore, but it does still not use the optimal strategy. So it is very important here to understand and to appreciate the difference between what this deep mind agent does and which something like Deep Blue did, which defeated Kasparov in chess. So with Deep Blue, there were a lot of chess grandmasters and a lot of programmers that programmed all of their understanding of chess directly to the agent, and then kind of the combination of all of this knowledge that it was given and immense computing power then sufficed to defeat Kasparov. Here the agent is not given any knowledge at all, so it does not know that there is a ball, it does not know that the ball should not go down. All it receives are the inputs of the pixels and its score, so how well it performed. And then it learns itself to recognize that there is a ball and that there is this kind of thing that it can move, that the ball tends to bounce on the wall and so on. It learns all of this itself, just much like a child learns to discover the world. So it's really this project. In fact, was published in Nature. And it is widely seen as a very important step towards broad artificial intelligence. So this deep mind that has defeated Kasparov in chess is kind of a prime example of an intelligence which has very high but very narrow intelligence. It can do exactly this one task. Now this is, by contrast, a very broad intelligence. It can in principle learn anything, and it has learned to play dozens of games like these. Okay, so then this brings us to the question, how long before we reach AGI here, meaning artificial general intelligence, so which is defined as an intelligence which would reach human levels on really almost all intellectual tasks. Now this question is very difficult to answer. There's absolutely no consensus among experts. So the only consensus there is that we cannot give kind of narrow timelines. We can only give broadish estimates. It depends on a lot of unknown factors. For example, will hardware or software eventually be the bottleneck? Will it be kind of a small team of genius programmers that do something in their basement? Or will it be a big government-sponsored Manhattan-like project? Are more speed bumps or accelerators ahead of us? So these are all very difficult questions with a lot of uncertainty. But having said that, the median estimate for a 50% probability of AGI is 2050, and for 90% probability is 2070. So the bottom line is that there's really a significant probability that it will happen within our lifetimes. Okay, so now here I had these terms speed bumps and accelerators. What could these possibly be? Now there are some things that could slow down progress. One of them is that it could potentially be that the progress that we have seen in recent years is simply due to us picking a lot of high-hanging fruits, and that all the problems that remain are just much more difficult than the ones that have been overcome in previous years. Then there's this Moore's law that Kaspar briefly talked about, which traditionally says that a lot of measures of computing power double every 2 years, and it may be that there's no reason to assume that this law continues to hold, and in fact there are some people who say that one now sees an end of this Moore's law, that the doubling time is now no longer 2 years but 3 years or so. Yeah, then of course everything which would stop technological progress would also stop progress towards artificial intelligence, so societal collapse. And finally, it may just be that humanity decides that it may not be a good idea to create agents which are more intelligent than humans. By contrast, that there are also a lot of factors that could speed up progress towards artificial general intelligence. So we have now much better hardware as we had in the past. So one factor here are these GPUs, which can do parallel processing in contrast to traditional CPUs. We have now much better algorithms for programming general intelligence. So this DeepMind, for example, that I showed before, uses what is called deep learning. So this is a heavily biology-inspired approach, which uses an artificial neural network. So it has, like in a biological brain, it consists of different layers of neurons, and it's called deep learning because there are a lot of layers of neurons behind each other. And then kind of the early layers of the network learn to recognize simple features, such as in this game before, that learn to recognize what a ball is. And then the higher level, the layers which are deeper down learn to recognize higher level concepts, such as it's a good idea to bring the ball behind this wall such that it bounces back and forth. And finally, we live in the age of big data, so we just have a lot of data available, which is very crucial for training these artificial neural networks. So every time you use Google image search and then Google for cat playing piano and then click on an image, then you train Google's neural network. You make it a bit better at recognizing images that show cats playing the piano. And finally, there are just a lot of incentives that make it likely that this progress will continue. So these are mostly economic in nature, but also of the military kind. Of course, nobody wants to fall back behind their competitors. So with this, I hand over to Kaspar.
So if these arguments hold up, I hope we convince you that this prospect of having superintelligence during our lifetimes kind of is a little bit fearful. So what can we do to avert kind of bad outcomes due to such superintelligence coming along the way? So kind of from an ethical perspective, if you look at different causes and you want to prioritize among them, there are 3 major criteria how you can do this. So first of all, you're interested in something that is of a large scope, so it should be an important issue. So why would you care about an issue that doesn't matter anyway? Then the issue needs to be tractable. So what you do needs to affect kind of the outcome or what is done about this issue. I mean, an issue could be very important and very large scale, but if there's nothing that can be done, yeah, so be it. And last, if you kind of look on your counterfactual impact, you want to have an issue that is not too crowded. So if there's already 1 million people working on an issue, kind of what the difference that you achieve will not be as high as if you're, for example, the 10th person that joins a very important cause. So the main message here is simple, so work on the matters that matter the most. And the argument is that AI is the key lever to the long future of kind of evolution as we know it. And the issue is urgent, it's arguably tractable, and it's totally uncrowded so far. And yeah, the stakes, so what at stake is astronomical, so it's literally the future light cone of our existence. Now, it's also important that we not only speak about kind of the negative effects of superintelligence. So if we manage this challenge well, so it might be very, very beneficial. So there's this concept of flow-through effects. So by going one level up, we could solve the difficulty of solving a problem. And artificial intelligence is a candidate for simplifying the problem solving that we currently are failing at. So if you look at other issues like extreme poverty, factory farming, climate change, artificial intelligence could help us in solving all of them, whereas each of the other one might even affect some of the others negatively, and this is not as drastic in alleviating kinds of problems we have there. Now, what needs to be done? So, with kind of this metaphor of an intelligence explosion, there's kind of this idea or project to just be first in building a friendly artificial intelligence before someone builds just any general artificial intelligence, so that we have a controlled detonation. Now the thing is, as I mentioned there, it's way more difficult to have kind of a friendly AI. Now one thing, or why is it difficult, is that if you have an agent that is more intelligent than you are, you need to make sure that you're not outsmarted by that agent. So there are kind of two broad categories of measures you can take. So one thing is kind of just try to restrain the capability of that agent. So one thing is, for example, by boxing the agent, kind of locking it up, or yeah, with other methods like tripwires, etc. And the other category is you let the agent free, but you make sure that the goals it pursues are beneficial to humanity and all other sentient beings. So even if we manage this well initially, there's no guarantee that an agent that is friendly initially, after several recursive self-improvements, is still beneficial in the end. So especially when you learn about the world, you might kind of have ontological updates, so your model might change, and kind of what you want to pursue, what is your utility function, might look different in the new model of the world. So these are totally open and challenging problems, and now kind of the more practical advice to all of you, or for those of you who will pursue a political career. So what we can do as a society is we can prioritize risk-reducing activities and progress over risk-increasing activities. And when it comes to artificial intelligence research, the message is that AI safety should outpace AI capability, and which you can see from this graph, this isn't the case at all right now. So it might be a good idea to change this inequality a little bit, at least. And the other thing is there are many uncertainties, as you've heard, regarding the timeline, regarding potential outcomes, etc. But what's sure is that we are the ones who will create such a superintelligent agent. So it's not primarily or not only a technical problem, it's also a societal one. So how can we ensure that we as humanity can cooperate? Because one of the most dangerous aspects of this whole topic are potential arms races among nations. And the danger of arms races is that parties sacrifice safety for speed. So it's more important to be the first one than to be safe. So what have we've learned during this evening? So we're standing in front of a very crucial crossroad for the future of this planet and maybe even this universe. So instead of just letting things happen, it might be a good idea to actively try to steer a course in that large space of uncertainty. And we have many, many open questions in philosophy, mathematics, and also when it comes to cooperation. So our track record as humanity in solving cooperation problems is very bad so far. And this is also the reason many people aren't optimistic about solving cooperation problem. That's why kind of the only hope might be in outpacing general artificial intelligence with friendly artificial intelligence. So I want to conclude this talk with a quote from the book called Superintelligence, which was written by this professor Nick Bostrom and was published last summer. So I'm going to read this. Before the prospect of an intelligence explosion, we humans are like children playing with a bomb. Such is the mismatch between the power of our plaything and the immaturity of our conduct. Superintelligence is a challenge for which we are not ready now and will not be ready for a long time. We have little idea when the detonation will occur, though if we hold the device to our ear, we can hear a faint ticking sound. So this is the end of this talk. You find the slides and many, many more references and charts and papers on superintelligence.ch. And if you have time, we also have time now for questions and answers. Thank you.